Hello, Mr. Burrell here. We're in the middle of Unit 3 talking about polynomials. We've talked about adding and subtracting polynomials and multiplying polynomials. We've talked about complex numbers and how they kind of mirror the same things that you can do with polynomials when it comes to adding and subtracting and multiplying. All that was kind of review. You've talked about that before. We've talked about that before. You've learned that before. Now we're going to go on and kind of extend what we know about polynomials and use what we've already learned to kind of extend that and further that a little bit. So we're going to start talking about the fundamental theorem of algebra along with finding complex polynomials, and we'll get to what that means here in just a bit. So objectives, this is what I hope that you're able to understand by the end of this lesson, by the end of this video. I want you to be able to tell how many solutions a polynomial has given that polynomial expression itself. I want you to be able to tell how many real, imaginary, and total solutions of a function has given its graph. So being able to tell solutions from the polynomial expression and from the graph, and then I'm wanting you to be able to identify the missing imaginary zeros or solutions of a polynomial. We'll talk about what that means, and be able to find the zeros of a factored function and state their multiplicity. All of these things are relatively new. Lots of these things you may have seen before, but not really known what it was talking about or what it's relating to. So these are the objectives for this lesson. Keep those in mind. This is how you're going to be able to know that you are successful with this subject. So, a little bit of a review from last year when you were taking Math 2. You would have seen a question like this. I gave you a graph and it said, find the zeros of the following function. Remember that zeros are also known as solutions of the function, or x-intercepts, roots. We call them lots of different things, but what we're talking about when we're talking about the zeros of a function is where that function crosses the x-axis. Most of the time we're talking about where that function crosses the x-axis. That's the easiest way to tell the solutions of a function. The reason we call them the zeros is it's when y is equal to 0. So if I had y equals some function, I don't know, x squared plus 3, when y is 0, we're going to fall right here. Here's y equals 0 along the x-axis. So every place where the function crosses the x-axis, those are my zeros, or the solutions. What do I call this graph? What kind of function does it represent? We talked about a bunch of different kinds of parent functions last year. Linear functions, quadratic functions, cubic functions, absolute value functions, etc., etc., etc. This function is going to be a quadratic function. Specifically, here is the formula for that quadratic function. Y equals x minus 2 squared plus 1. Quadratic means I have an x squared in there somewhere. And you notice here that I have two solutions to this function. That's going to come in handy here in a little bit. Okay. So, using that concept right there, we're going to start talking about the fundamental theorem of algebra. This is like one of the most important things you'll ever learn in algebra, and this is kind of the basis behind what everything we do in algebra with polynomials and with functions like this. So the fundamental theorem of algebra states, any polynomial of degree n has n roots. What does that mean? N is just a variable, so it can be any number. So any polynomial of degree 1 is going to have one root, or one solution. Any polynomial of degree 2, put a 2 here, any polynomial of degree 2 is going to have two roots, or two solutions. Any polynomial of degree 3 is going to have three roots, or three solutions. Any polynomial of degree 76 is going to have 76 roots, or 76 solutions. That's what the fundamental theorem of algebra says. It ensures that any function that you have, any polynomial, the degree of that polynomial is going to be the same number as the number of solutions that function has. So like right here, y equals x plus 4, well, that's really easy to be able to determine how many solutions that's going to have. If I plugged in some value for y and solved for x, I would only get one answer. That's just a straight line. I'm just going to get one solution. The degree of this polynomial is 1, because there's no exponent here. It's just a 1. So x to the first power, there's going to be one solution here. function where the largest exponent is x squared, this 2, that means I'm going to have 2 solutions. A polynomial of degree 3 is going to have 3 solutions. A polynomial of degree 17 is going to have 17 solutions. So again, any polynomial of degree n has n roots. Whatever the degree of the polynomial is, that's the same number of roots as it is going to have. Remember that a 0 is a value of x which makes the function equal to 0. So like right here, if I put y in for 0, 0 equals x plus 4. If I solve for x, my answer is going to be x equals negative 4. One solution. That's all I have, right? And we're going to talk about these problems more in the upcoming units and the upcoming lessons. But when I go about solving a problem like this, if I set y equal to 0, eventually I'm going to get 2 factors giving me 2 solutions. Here I'll have 3 solutions, 17 solutions, etc., etc., etc. So that's a big thing I want you to get. Whatever the degree of the polynomial is, that's the number of solutions or roots that function is going to have. Okay, so in your guided notes, I have this question here. So right off the bat, before I even pop up the pictures on here, let's determine how many total solutions each of these polynomials is going to have. So in order to determine that, I need to look at the degree. So this is a degree 1 polynomial, this is a degree 2 polynomial, this is a degree 3 polynomial. So I'm going to have 1 solution here, 2 solutions here, 3 solutions here. That's how many solutions there are going to be. If I look at the graphs, I can also determine the number of solutions by looking at where the graph crosses the x-axis. So this graph crosses right here. This graph crosses there and there. This graph crosses in 1, 2, 3 places. So it's really easy to see that this function has 1 solution, this function has 2 solutions, this function has 3 solutions. Since I can actually pinpoint where those functions cross the x-axis, I can say that those solutions are real solutions. They actually cross the real number line, this real x-axis here, so those solutions are going to be real numbers. Namely, this is like negative 1-ish, this is like negative 2, positive 2, this is like a little bit less than negative 3, like negative 1.5, positive 1. I can actually pinpoint those solutions there. Okay, let's step it up a little bit. So complex numbers, we just finished in section 2 of this unit talking about complex or imaginary numbers. So when a polynomial function does not cross the x-axis, does that mean the fundamental theorem of algebra no longer exists? No, it doesn't. The fundamental theorem of algebra is all-encompassing. It doesn't lie. So if I don't have real zeros or real solutions to a polynomial function, the roots of a polynomial are going to be imaginary or complex. So if the function does not cross the x-axis but still has solutions, those solutions are going to be imaginary or complex numbers. Imaginary roots will always come in groups of 2 and are conjugates of each other. We talked about conjugates a little bit, which basically means that if I had the root positive 2i, another root or another solution to that polynomial function would be a negative 2i. The example I gave in the last lesson, if I had like 3 plus 7i, the conjugate or the opposite solution would be 3 minus 7i. They always come in groups, they always come in pairs that are conjugates or really opposites of each other. So let's take a look at this. Again, I have 3 graphs. I want you to state the number of total, real, and imaginary solutions. So first, let's just determine how many total solutions there are going to be. This is a polynomial of degree 3, polynomial of degree 2, degree 3, and degree 5. So there are going to be 2 total solutions here, 3 total solutions here, 5 total solutions here. Okay. Next, I can determine the number of real solutions by how many times my graph crosses the x-axis. Well, here's the x-axis right here. Where does that graph cross the x-axis? Nowhere. So there will be 0 real solutions. On this graph, how many times do I cross the x-axis? 1. So there will be 1 real solution. On this graph, how many times does this graph cross the x-axis? 1. So there will be 1 real solution. So again, the fundamental theorem of algebra says that the total number of solutions is equal to the degree of the polynomial. So since there are 2 solutions here and 0 of them are real solutions, that means both of those solutions must be imaginary. There will be 2 of them. If in this case there are 3 total solutions and only 1 of them are real, that means 2 of those solutions will be imaginary. If here I have 5 total solutions and only 1 of them are real, that means 4 of them will be imaginary. Okay, that's the fundamental theorem of algebra. Whether the solutions are real or imaginary, there will be the same number of solutions as the degree of the polynomial. Okay, let's talk about repeated roots or multiplicity. What does that mean? When I talk about multiplicity, is just the number of times a specific factor in a polynomial makes the function 0. So if you remember, let me explain that a little bit. If you remember back to Math 2, we talked about the zero product property. That when 2 factors multiply together and equal 0, at least one of those factors is going to have to be equal to 0. So x minus 2 is going to have to be equal to 0, or x plus 5 is going to have to be equal to 0. It's x plus 5. So then my solutions end up being positive 2 and negative 5. Those would be my solutions. But notice here, I have x minus 2 times x plus 5 squared. Squared just means I'm multiplying something by itself 2 times. So I can rewrite this as x minus 2 times x plus 5 times x plus 5. There's 2 of these. There's 2 x plus 5 factors. So that means technically this solution, this 0 of negative 5, is here twice. It has a multiplicity of 2. There's 2 occurrences where negative 5 is going to be a solution to this function. So right here, this x squared means that there's going to be a multiplicity of solutions in this specific factor. So in this case, x plus 5 squared means that the solution of negative 5 pops up twice. Let's look at this in real time. So again, I'm having you state the number of total, real, and imaginary solutions. Let's not look at the graphs for now. Let's just look at the functions. I can automatically tell how many total solutions there are going to be based on the degree or the highest exponent of these polynomials. So here there are 2 solutions, 2 solutions, 3 solutions. Well, notice on each of these functions are kind of unique when they're when they're going across the x-axis. They're not actually crossing here. This is kind of just touching and going back up. This function is just kind of touching, going back up. This one doesn't change direction at all. It just kind of rests here on this function here on the x-axis. The way it behaves that way is because of the way these functions are set up. Each of these are going to be have solutions that are multiples. They're going to have a multiplicity of solutions. So here I have, it looks as if I only have 1 real solution, but really I have 1 real solution repeated twice. That solution is going to be 0. So there's 2 real solutions, but they're just both 0 because there's a multiplicity there. Here it looks like there's just 1 solution, a positive 4, but there's 2 solutions here, so it's really a positive 4 repeated twice. X minus 4 times x minus 4. There are 2 solutions there, 4 and 4. Here I have x minus 2 cubed, so there are 3 solutions, and all of the solutions are going to be the number 2. Right here at 2, all the solutions are going to be 2. So it's just the same solution multiplied, a multiplicity of 3. Okay. So, here I have just a bunch of different examples. It says, state the zeros of each function and their multiplicity. Let me move that out of the way. So when I'm talking about the zeros, again, what number would make each x value equal to 0? And then what is its exponent? So we'll go ahead and kind of set this up. What are the zeros? And what is the multiplicity? So here my zeros are going to be 2, because if I were to set this factor equal to 0, I would get a solution of 2, and my factor here would be -6. So my zeros are 2 and -6. What is the multiplicity of this solution, this factor? The exponent's 2, so the multiplicity is 2. It's going to happen twice. Right here, x plus 6 cubed, I have a 0 of -6, so that solution is going to be multiplied 3 times. Okay, let's go down to this one. What are my zeros, and what is the multiplicity of each of those zeros or each of those solutions? So I have this x factor, and this x factor. So this one's not being added or subtracted by anything, so the 0 is just 0. The solution is 0. The solution here is going to be 4. The solution here is going to be 1. Those are my different solutions, because those are the values that when I plug them into this equation, it makes one of these little factors equal to 0. Well, how many times is this 0 being multiplied? None. There's no exponent. It's just 1. The 4 is being multiplied 4 times, and this factor is just being multiplied 1 time as well, so that's it. Let's go look at this one right here. Let's look at 4. Let's look at the zeros and the multiplicity. What are the zeros here? Well, I can't plug any value in here. There's no x's. So what x value could I plug into each of these factors to make those equal to 0? Well, I can plug in a -7 here, a +3 here, and a +8 here. The multiplicity here is 1. The multiplicity here is 5. That happens 5 times. And the multiplicity here is 8. 1. Sorry, the exponent here is 1. The solution is 8. Okay. So that's how we determine the zeros of a function and their multiplicity. The last section here I want to discuss is finding additional zeros. So if a polynomial has the following zeros, find all additional zeros. So without a function, it can be kind of hard to determine what the zeros of that function are. But if I'm given a complex zero or a complex solution to a function, I know from what I mentioned earlier, and let me move my face out of the way here, that anytime you have a complex solution, there is automatically going to be 2 of them. They will be conjugates of each other. They will be opposites of each other. So here it says, what part of the complex number comes from the square root? Find the conjugate of each complex number. So remember that a complex conjugate is the number with an equal real part and an imaginary part, equal in magnitude but opposite in sign. Blah, 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 blah. Let me explain what that means. So if I have this complex solution, 1 minus 5i, the conjugate, or the other complex solution, is going to be 1 plus 5i. The real number stays the same. The imaginary number switches signs. If I have these two solutions, 3 plus I, the conjugate is going to be 3 minus I. -2 minus I is going to be -2 plus I. So now this polynomial, if these were the solutions, this polynomial would have 5 solutions. This polynomial would have 4 solutions. This one I have -3 plus I, so the conjugate, the other solution, is going to be -3 minus I. This is just a 4i, so the conjugate is going to be -4i. Remember, the real part of the imaginary number, the imaginary number in the complex number switches signs, so this becomes a -4i. The other solutions here would be -3 plus 2i, and the other solution here would be -3 minus 2i, but notice that those solutions are already included, so I don't need to write them again. And then the other solution for a positive 6i would be a -6i. So that was kind of a lot of information, but going back here to the very beginning, the big thing that we need to remember is that any polynomial of degree n, so whatever the highest degree, the highest exponent in the polynomial, whatever that degree is, whatever that number is the same as the number of solutions or roots that polynomial will have. It's almost like a cheat sheet for you. Whenever you're in doubt about if you found all the solutions, this will tell you how many solutions there should be. So these are the concepts I wanted you to understand by the end of this video. Tell how many solutions a polynomial has given the expression and given its graph, finding missing imaginary zeros, and finding the zeros of a function in factored form, and stating their multiplicity. I hope that was helpful. Please reach out to me if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.